Okay, now let's move to our second topic about machine scheduling problems. So in many cases, we need to assign jobs or tasks to machines. Okay, for example, suppose you are running a factory and you are producing one single product, or it doesn't matter, or you are producing for a few customers. Okay, you have only one machine, and that machine does serial production. That means at each moment you can only process one job. Each job has its due date, and for each job there is a certain amount of time that you need to pay on that machine so that you can finish that job. Then your question would be just, for example, how to schedule these n jobs to minimize the total number of delayed jobs. Okay, if you have too many jobs and the due dates are too close to today, then probably you cannot finish all those jobs by their due dates. Then for some jobs, they get delayed, and you want to minimize the total number of delayed jobs. Okay, so that's just one kind of examples. In this example, scheduling is nothing but sequencing. Okay, sequencing means you decide the orders to work on these jobs. Okay, that's because splitting jobs is not very helpful, right? If you start to work on one job, you should try to finish it as soon as possible because you only care about when a job is completed. Or alternatively, you simply should work on another job instead of work on this for a few moments and then work on that for a few minutes without completing anything. Okay, that's not useful. So once job splitting is not helpful, the total possible ways to schedule your n jobs is just n factorial. Okay, so at least there's one way to solve this problem is to try all those n factorial ways to see which one is the best. Okay, and then of course that's too time consuming, so you may want to ask whether there is a polynomial time algorithm or not. Okay, for all different kinds of machine scheduling problems, some have polynomial time algorithms, but many of them do not. I mean, people believe that does not happen. Okay, but they somehow share one single characteristic. Most of them can really be formulated as integer programs. So once you have your integer programming capability as your tool, you really can handle a lot of different kinds of machine scheduling problems. Okay, so that's our purpose today, to use integer programming to deal with machine scheduling problems. Of course, machine is just a concept. Okay, it may be factories, maybe workstations, or even maybe workers. Okay, sometimes you assign jobs to workers. So machine in this lecture just means those resources that can help you process jobs. Okay, so it's just a concept. Machine scheduling problems can be categorized in multiple ways. For example, we talk about different production modes. Sometimes you have only one single machine. Then, yeah, it's always serial production. Sometimes you have multiple machines. In one situation, you are talking about parallel processing. For example, you probably have, let's say, 3 machines, and you say you have n jobs. Alright, so let's work on job 1 here while we are working on job 2 there, and we are to work on job 3 there, and maybe this is job 4, job 5, job 6, and so on and so on. Okay, this is your machine 1, 2, 3. So in this particular case, parallel machines means each machine is unrelated to another, and each job is unrelated to the others. Okay, they can be processed parallelly. You also have flow shop and job shop problems. They are problems with multiple machines and the multiple stages for each job. Okay, so consider the following case. For flow shop, that means for each job, you have a few stages. You need to first pass machine 1, and then machine 2, and then machine 3, and so on and so on. Okay, a very typical assembly line fits this situation. Okay, all those assembly lines in a factory are flow shop problems because there are multiple stages. So when you try to graphically depict them, then it would be something like this. Okay, suppose these are machines 1, 2, 3 for stages 1, 2, 3. Then when you work on job 1 here, you cannot start job 1 on the second and the third stages. You can start the second stage of job 1 only after stage 1 has been completed, and for the next stage is the same thing. Okay, then you probably want to work on job 2. Then sometimes job 2 must wait for a while before you can start running the second stage because job 1 is still there. And sometimes after you complete a stage, you need to wait for a while until you can process the next task, like here. Okay, so flow shop obviously is more complicated than parallel problems. Or you even have job shop problems. That's when different jobs may pass through those machines in different orders. Job 1 may require machines 1, 2, 3, and the job 2 may require machines 3, 1, 2, and so on and so on. So the problem gets even harder. You probably face job splitting issues. Sometimes you have non-preemptive problems. That means once you initiate a job, you need to finish it. You need to finish it. And between the starting and finishing time, you cannot insert any other task. Sometimes you have the preemption option. That means you can work on this job for a while and then stop it and work on another job for a while and then come back to the original job. Okay? Sometimes this is useful, especially when you are working on flow shop or job shop problems. Then those switching or job splitting may help you to utilize those residual capacities like here, okay, to minimize your idle time. Sometimes you talk about performance measurements. That typically gives you different objective functions. For example, you may talk about make span. Make span is a special word for scheduling. That is the time that all the jobs are completed. Okay, make span. So it's the completion time of the last job. Sometimes you talk about total completion time. Completion time is for the job to be finished. Okay, so you want to finish all the jobs as soon as possible, in the sense that you want them to be completed, so that the total completion time is minimized. Sometimes you want to minimize the number of delayed jobs. Sometimes you want to minimize total lateness. Sometimes you want to minimize total tardiness. Okay, these two seems to be similar, and we will tell you what's the difference later. But anyway, you really have different kinds of machine scheduling problems, and the scheduling itself is a subject. Again, that even a full semester course is not enough. But anyway, we will give you a tool, integer programming, to deal with it. Let's start with this example, minimizing total tardiness on a single machine. Suppose we want to schedule n jobs on a single machine. For each job j, I have been given the processing time pj and the due time dj. Processing time means I need this amount of time to complete this job, and the due time is a requirement for me to satisfy. And then different schedules gives these different jobs different completion times. Okay, the completion time denoted as CJ means a particular time moment that this job is finished. Then with CJ and DJ, we define the tardiness of a job as the following. Okay, if CJ is greater than DJ, that means you complete this job after its due date. Then the tardiness is the difference between the two times. But if you complete a job before its due date, then the tardiness is 0. Okay, this is just different from lateness in this field. Lateness in this field is just the difference between Ci and Dij. CJ and DJ. So that means Cj minus Dj may be negative. Okay, if you complete a job right before your due date, then in some sense you are getting some rewards. But when we talk about tardiness, we don't. Okay, as long as you can finish a job in advance, then you just get no penalty, but you don't get any reward. You only have one machine, and that machine can process only one job at a time. Okay, so how would you schedule all the jobs to minimize the total tardiness? Okay, that's the objective here. We don't want to talk about whether this problem can be solved in polynomial time or whether there is any good useful algorithm for that. We only want to use integer programming. So let's try to look at this problem. Cj is our decision variable. Okay, and how are those Cj's relate to each other? Well, let's see it. Suppose we schedule jobs 1, 2, 3, and 5 and n in the order. So that means we work on job 1 first, and then job 2, and then job 3, and finally job n. Then a relationship we will have is here. C1 would just be P1 because we start at time 0. And then after a few amount of time, we complete that job. For C2, it becomes P1 plus P2. We use P1 to finish job 1 and then P2 to finish job 2. And the Cn blah blah blah. Here we can use a so-called Gent chart to help us illustrate this schedule like this. Okay, so I have a machine and I start the machine by working on job 1. Then this would be P1, and that's why this is C1. Then I spend some time to work on P2, job 2. So my C2, very clearly, C2 would be P1 plus P2. And then I probably work on P3, and P3 may be short. Then my C3 would be here, and so on, and so on. And that's a depiction of our schedule and the processing time and the completion time. Obviously, splitting jobs, again, does not help in this problem. Okay, please convince yourself why that is true. Okay, so now, obviously, this is just one option, okay, to schedule jobs one by one, or first come, first serve. That's just one option. But you want to ask whether that's optimal. So you want to search among all the possible relationships. So let's consider the following. The machine can actually start job 2 only after job 1 is completed, okay, in this particular order. So that means we have C2 greater than or equal to C1 plus P2. And here, because there is no other job in between 1 and 2, so that's why this is actually an equality, just like here, okay? But in general, if job 1 is put in advance to job 2, you have a relationship like this, okay? But of course, the difficulty is that how do you know that in an optimal solution, job 2 should be put after job 1? You don't know it. So you need to make sure that in your formulation you are not excluding this possibility. So in the next video we tell you how. Thank you.